All right, thank you, Dr. Savaljo. Sorry, I'm a little bit ill, so my voice might be a little bit smarring. And let me see if it works. Okay, good. So today I'm going to talk about something a little bit different from what most people do in here. Because most of you are doing physics, so you do the modeling to explain, to interpret the aging. But for people like me, because we are in the broader term of geroscience, we not only want to identify and explain the aging, interpret it, we also want to solve it. So the aim of the geroscience is not only to find the ways to describe aging, but also to find a way to slow or even reverse it. So there are many ways to actually do this, achieve this, but today I'm just going to talk about one topic, which is small molecules. And we term them geroprotectors, which the gero means old in the Greek or Latin, I don't remember. But these small molecules have been shown to extend lifespan in many model species, from low, such as yeast, to other higher, such as mice. So these are the. So why do we choose geroprotectors rather than other therapeutics? One major reason is that it's easier for the clinical studies because many of them have been proposed for other diseases, and many of these diseases are known to be age-associated, such as like diabetes, Alzheimer's disease. Okay, and there are many geroprotectors, and here we have some populars, such as metformin and rapamycin. I know some people are haters of metformin, but still, we are having a really limited number of geroprotectors. So there are many ways to discover geroprotectors. This is mostly in the in biology. So one way is you do the drug screening, and the second way is that if you know in biology that there are certain targets that are known to be associated with longevity, such as mTOR complex. So once you know these drug targets, you can actually design drugs for these targets, such as like rapamycin. We know that rapamycin is an mTOR inhibitor, so we can design more potent and mTOR inhibitor. But the thing is that whatever you design, it's still mTOR inhibitors. So the negative effect you got from inhibiting mTOR will still be inherited, mostly inherited. And today I'm going to talk about a third method, which is a more recent method, which is the genetic-based prediction. So what's genetic-based prediction? It's basically to use the transcriptome to predict the effect of the drugs. So so the idea is actually pretty simple. You have a certain transcriptomic signatures that you want to match with. And then you look for the database of the drugs to see the drugs that can actually match or mismatch your signatures. And here we term these signatures as longevity signatures. So once we target these longevity signatures, the drug we found were likely to be potentially geroprotective. Okay, but the question is, how do we obtain these longevity signatures? So there are basically two ways of doing it. The first one we call it mimic approach, which is mimicking the known geroprotectors. And back in the days, people do like mimicking the calorie restriction. And this is a really elegant paper from Gladyshev lab that he actually do the consensus transcriptomic signatures of many interventions. And then they use these interventions to predict the drugs that have that produce a similar transcriptomic profile. But the thing is that this is likely to predict the drug with similar mode of action. For example, if my memory is not wrong, writing this paper, they test 4 drugs, and 2 of them are actually still mTOR inhibitors. And the other way is reversal approach. So the idea is very simple. You see what's changed during aging, and you try to reverse it. So people believe that if your geroprotector can reverse the aging transcriptome, you're likely to rejuvenate your cells. But this is an unvalidated assumption that reversing aging transcriptome signature is beneficial. So we want to test whether this reversal approach is correct. So does geroprotector reverse the aging transcriptome? So we use the C. elegans. If you heard Professor Yang's talk yesterday, and these are really simple model species for anti-aging interventions. So we have these worms from day 6 to day 18, which is literally the late stage of their life. So we perform the principle, this is a general step of building this PCA-based transcriptomic clock. And we found that this clock actually accurately predict the altered biological age of these mutants. For example, this is devastating loss of function, which are short-lived and is predicted to be biological order. And this is E2 mutant, which are mimicking the dietary restriction. And we found that it's biologically younger. But when we think about the drugs, what's actually happening is that these worm treated with lifespan extending drugs are mostly predicted to be older, except rapamycin. So we can see that individual drugs are mostly predicted to be older, and there are lifespan extending drug combinations, and they are predicted to be even older. So why is this happening? So one explanation is that during the aging there is adaptive process that are activated in response to this accumulation of damage. And these geroprotectors will actually activate these pathways. And what will happen is that once it's activated, you are going to have a long-time protective effect on the C. elegans. But because these are also activated during aging, so your worms will be predicted to be biologically older. So now the question is, how can we actually deconvolute the aging transcriptome to actually extract these from this complex transcriptome instead of just using the PC as a representative of the aging? So what we can do is that we build this aging network, and we have the worms with different ages and worms with devastating mutations. So we build this network based on their co-expression. So this is exactly what Dr. Ho talked about, the scale-free network. So we have this, we build this network, and then we see that if a module, which is the co-expressed genes, if this module are expressed, their expression change during aging are exactly are different from their expression change upon loss of devastating and vice versa. It's likely to be a positive adaptation or negative adaptation. And these genes are likely to be, for example, stress response. And also in this network, there will be modules that are representative of biomarkers, or they're just like the failure of adaptation, like they are the causative of aging. So we call these modules that are causing the pro-aging damage production as aging modules, and modules that respond to the pro-aging damage as longevity modules. Okay, and this is basically a framework of what I have been doing. So first of all, we build this network using this data set, and then what we do is that, how do we know that what module is associated with is beneficial or bad? So we take the public data set, and then we extract the reported median lifespan of each condition, and then we give these modules a representative score using the GSV algorithm, and then we associate their GSV score with their reported median lifespan. So if a module is a longevity module, which means pro-aging, so it means that its activation should lead to a longer expected reported median lifespan. So they will be positively associated with median lifespan, and then we can actually aggregate these data sets and then perform meta-analysis to find these conserved consensus longevity associated modules. And then we take these longevity associated modules. We also try to see if they're preserved in higher order species, and we use those modules that are mostly preserved in higher order species or have the strongest association with longevity. And then we take 3 pro-longevity modules and 2 anti-longevity modules, and then we take their hub genes. And you remember in the scale-free network, hub genes are the genes that have the highest number of connections. And then we take their hub genes to actually query the connectivity map, which is the database of drug-induced transcriptome. So when we query these modules with CMAP, what we can clearly see that there are drugs that actually activate these longevity modules, meanwhile suppressing these aging modules. So these modules actually have a lot of known class of geroprotectors, such as HDAC inhibitors and HSP inhibitors, which is and then basically what we do next is that we do an in-depth screening on 15 potential geroprotectors, and we found that 10 out of 15 can significantly extend lifespan of C. elegans. And this is the conclusion, and that's all. Thank you for listening.
Time for only one question. Anybody? Okay, if no questions, thank you very much for your talk.